So now let's do some specific examples of things that you would have to do for the homework or on the AP exam. So we're asked to find the Taylor series for e to the x with a equals 2. And so here's just a reminder of how I do. This is, I wrote for e to the x, but what I wrote here is just the general Taylor series. And this is what you really have to know for that exam. So it's the sum from n equals 0 to infinity of the nth derivative at a over n factorial times x to the n. So what we want to do, if we want to actually write one of these out, we have to know what f of whatever the a value they gave us was. This time a equals 2. So we want f of 2, and we're going to want f prime of 2. And we want to lay out enough of these that we can get the pattern. So let's put out a couple of them and just see what it looks like. Equals. It's also common on the AP exam that they will ask you for a specific number of terms. So instead of laying out the entire infinite series, like if they say 5 terms, we would do 5 of them, right? So this is asking you just for the Taylor series. So the series, like, it's a good time to mention that if I do finitely many terms, that's called the Taylor polynomial. And if I do infinitely many terms, that's called the Taylor series. So series has infinitely many terms. A polynomial has finitely many terms. All right, so what are all these things? Well, I have e to the x, so f of 2 is e squared. And remember, I'm doing, over here, this is the function. I'm doing the derivative of e to the x. I'm not doing the derivative of e squared, because that would be 0, and then they'd all be 0. I'm doing the derivative of the function. So f of x is e to the x, f prime is e to the x, f double prime is e to the x. All the derivatives are e to the x. That means that all the f whatevers of 2 are e squared. Right? But then don't forget that you got to get the n factorial in there, because what we have here is just this numerator. So I usually write what are the c sub n's. We're going to chart entry for the c sub n's. I have e squared over 0 factorial, e squared over 1 factorial, e squared over 2 factorial, e squared over 3 factorial, and e squared over 4 factorial. All right, so, I can sort of simplify some of these a little bit, but I don't think it's very helpful because we got to write the summation form anyway. So then remember that for this is a Taylor polynomial, so it's not x to the n, it's x minus a to the n. I'm glad I caught that. All right, so see, I'm nothing without my students to catch me in my error. See, it's just not, I don't know. It's not the same, my friends, but I'm sure we'll see each other someday soon. So here we go. We're going to do x minus, our a is 2, so x minus 2 to the 0, x minus 2 to the 1, x minus 2 squared, x minus 2 cubed, and x minus 2 to the 4th. Right, so this is just always going to stay a all the way down. This is a all the way down. We have n equals 0, 1, 2, 3, 4. N equals 0, 1, 2, 3, 4. All right, so then we just put that together and say, so my e to the x is equal to, I can write out some terms. The first one's going to be e squared, and then I'm going to have e squared x minus 2, and then I'm going to have e squared x minus 2 squared over 2. We don't really have to do that. You can jump straight to the fact that e to the x is equal to the sum from n equals 0 to infinity of e squared over n factorial times x minus 2 to the n. And now we've accomplished what it says. We found the Taylor series. That's the Taylor series at a equals 2. That's it. So that's some of the kind of things they're going to be asking you to do. I'll just point out, I got this example out of the book. There's something about it that bugs me, though, like in terms of utility. If I wanted to compute something like e to the 4th, the problem is you don't have an exact value for e squared to begin with. We don't know what e squared is exactly. So using this process to calculate other values of e would be calculating unknown values of e just based on another unknown value of e. So in this case, you'd really, the only truly known value of e is e to the 0, because we know it's 1, right? Even e to the first power, you have to have some way of knowing what e is. And that is going to be some other iterative process. So arguably, I think Maclaurin series is the only thing that makes sense with e to the x. Whereas with sine of x and cosine of x and some other things, we're going to look at a cube root function next. It makes sense to be looking at some other value of a other than 0. But that's how you can do that one.